Bula, and welcome to this UNESCO Masterclass series session on climate change and the Pacific Islands. My name is Awnesh Singh, and I'm from the Pacific Center for Environment and Sustainable Development at the University of the South Pacific. In this session, we will look at tropical meteorology and physical oceanography in the tropical Pacific region. Our learning outcomes for this lecture are to understand the climatic conditions of the tropical Pacific region, describe how the atmosphere and ocean responds to ENSO events, recognize the impacts of ENSO events on South Pacific Island countries, and appreciate the probable impacts of climate change on naturally occurring events like ENSO. Approximately 70% of planet Earth is covered by water. These waters can be divided into the 5 oceans: Atlantic Ocean, Indian Ocean, Pacific Ocean, Arctic Ocean, and the Antarctic or Southern Ocean. In this talk, we will be concentrating on the Pacific Ocean, and in particular the tropical Pacific Ocean. The tropical Pacific region is defined here as the region encompassed between 30 degrees north and 30 degrees south and bordered in the west by Southeast Asia and Eastern Australia, and by the west coast of North and South America in the east. Most of the western tropical Pacific region is dotted by small islands including Solomon Islands, Vanuatu, Fiji, Tonga, Samoa, Niue, Cook Islands, French Polynesia, Tuvalu, Kiribati, Nauru, Marshall Islands, Federated States of Micronesia, Palau, Tokelau, New Caledonia, Wallis and Futuna, and Guam. Like other countries, these small islands are subjected to seasonal fluctuations in climate, and today I will briefly describe the main driver of tropical Pacific variability in this region. To set the context, it is important that you understand the climate of the tropical Pacific region. The southeast and northeast trade winds blow from the eastern Pacific towards the western Pacific along the equatorial region. These trade winds are known as the easterlies. As these winds move above the surface of the water, they move the water in the same direction it is blowing. As a result, the warm surface waters are carried across from the eastern Pacific towards the western Pacific. This results in a piling up of water in the western Pacific region. These piled up waters constitute some of the warmest waters found in the world and can reach temperatures up to and or above 30 degrees Celsius. This region of warm waters is known as the warm pool region. In contrast, because of the vacuum created in the eastern Pacific due to the westward movement of surface warm waters and the strong Peruvian current along the South American coast, cold and nutrient-rich waters from below the ocean move to the surface in the southeastern Pacific region. This process is called upwelling. The upwelling of these cold, nutrient-rich waters provides food for thriving fish and bird populations. The map of the sea surface temperature, or SST, in the tropical Pacific Ocean shows the location of the warm pool and upwelling region off the South American coast. 2 wide bands of warm waters can be seen which lie underneath the zone of converging winds. The Intertropical Convergence Zone, or ITCZ, lies just north of the equator, while the South Pacific Convergence Zone, or SPCZ, lies obliquely and stretches from near Papua New Guinea towards French Polynesia. The ITCZ and SPCZ both meet in the warm pool region. These features are modulated by the seasonal fluctuations, meaning that they move according to the seasons. The converging zones are also regions of increased precipitation, and so seasonal changes in their position also drives precipitation changes. This is what affects the climate of the South Pacific Island countries, which mostly have either a dry or wet season depending on the position of the SPCZ. The warm pool region is an area of increased convection because of the warm waters there. Hence, there is an upward motion of warm air that has been heated by the warm waters underneath it and is characterized by low atmospheric pressure. The warm air carries moisture into the upper atmosphere and creates deep convective clouds which eventually precipitate in the warm pool region. At the top of the atmosphere, the warm air loses its energy due to condensation and moves eastwards before it sinks in the eastern Pacific region, characterized by high atmospheric pressure. This path of moving air creates a convective circulation and is known as the Walker circulation. In the ocean, because of more warm waters in the western Pacific than in the eastern Pacific, a region called the thermocline, which separates the upper ocean from the deep ocean and can be represented by the 20 degrees Celsius isotherm, slopes up towards the east. This thermocline structure is only evident within about 5 degrees of the equator, beyond which the thermocline rises towards the surface because of cooler waters found away from the equator. These basically describe the climate of the tropical Pacific region in terms of atmospheric and oceanic features. These mean conditions are, however, modulated by one of the main and well-known drivers of climate variability in the region and around the globe, that is, the El Niño Southern Oscillation or ENSO phenomena. As the name suggests, the El Niño Southern Oscillation phenomena oscillates between two distinct phases, the warm El Niño phase and the cool La Niña phase. El Niño events eventuate basically due to a weakening of the easterlies. Remember, it is the easterlies which pile up the warm waters in the Western Pacific warm pool region. A weakening of these easterlies results in the subsequent release of these piled up waters from the warm pool towards the east. As a result, warmer waters are now found in the central and eastern basins. Because the volume of warm water in the warm pool has decreased, the thermocline there shoals. Because the volume of warm water in the warm pool has decreased, the thermocline there shoals. In contrast, because of more warm waters entering the eastern basin, the thermocline there deepens. These processes cause the equatorial thermocline to flatten. Note that the thermocline sloped up towards the east during normal conditions. The weakening of the easterlies can be attributed to westerlies originating in the Western Pacific. These westerlies are a result of the Madden-Julian Oscillation, or MJO, and westerly wind bursts. The wind regimes in the Western and Eastern Pacific allows for a weakening and subsequent modification of the Walker circulation due to the decrease in the east-west gradient of sea surface temperatures along the equator. Note that this feedback between the atmosphere and ocean is necessary for the onset of ENSO events. Note that this feedback between the atmosphere and ocean is necessary for the onset of ENSO events and is known as the Bjerknes feedback. Because the warm pool has extended towards the central basin, it is now the location for increased convection, where warm air rises to the top of the atmosphere, from where it travels either to the east or west before sinking in the western or eastern Pacific, respectively. Because the warm pool has extended towards the central basin, it is now the location for increased convection, where warm air rises to the top of the atmosphere, from where it travels either to the west or east before sinking in the western or eastern Pacific, respectively. El Niño events also cause a southward movement of the ITCZ, so that it lies closer to the equator. The east end of the SPCZ moves north from its normal position, so that it is now lying horizontal and close to the equator as well. In fact, the ITCZ and SPCZ can be said to have converged at the equator. The magnitude of surface warming in the central and eastern basins determines the strength of the El Niño event. Surface manifestations of warming are usually shown using sea surface temperature anomalies. Anomalies are the difference between the current and normal conditions. The typical signature of El Niño events can be represented by sea surface temperature anomalies, which show a tongue of warm water that originates along the South American coast and straddles the equator from the eastern to the central Pacific basin. A large El Niño event may have anomalous warming of up to 3 degrees Celsius in the central eastern basins, as was the case during the 1982-83 and 1997-98 events. However, it should be noted that no two El Niño events are quite alike. Each event is different in terms of its onset time, duration, magnitude, and position of anomalies. Also, El Niño events tend to peak at the end of the year or during austral summer. Although El Niño events occur in the tropical Pacific region, its impacts are felt globally. In the western South Pacific region, for example, because of the northward movement of the SPCZ, the main rainfall producing band in this region, many countries, example Fiji, Tonga, New Caledonia, Vanuatu, etc., that lie under the normal SPCZ position now face periods of less rainfall. Note that this would normally be their wet season. As a result, El Niño events tend to create drought conditions for these countries. However, other countries, example Tuvalu, Kiribati, Tokelau, etc., which lie northwards of the normal SPCZ position now receive more than the usual amount of rainfall because of the close proximity of the SPCZ. This may result in flooding in those countries. Hence, El Niño events affect different areas in different ways. The opposite phase of El Niño is known as La Niña. During La Niña events, the easterlies strengthen and the warm pool is pushed further to the west and lies above the Australian continent. The upwelling along the South American coast increases due to the stronger than normal southeast trade winds. This creates a stronger east-west gradient of sea surface temperature along the equator, which acts to further strengthen the easterlies, the Beeknes feedback. As a result, the Walker circulation strengthens and its ascending branch is found further west of its normal position. The thermocline slope steepens such that the thermocline is found deeper in the western basin and closer to the surface in the eastern basin. The ITCZ moves further north of its normal position and the SPCZ moves southwestwards from its normal position. For countries in the South Pacific region, this means more rainfall, and for those countries more towards the north, it can mean drought-like conditions. Like for El Niño, the magnitude of surface cooling in the central and eastern basins determines the strength of the La Niña event. The typical signature of La Niña events are basically the opposite to those during El Niño, with the tongue of warm water now replaced by cooler upwelled waters. So, these are the major drivers of climate variability in the tropical Pacific region. But please do not confuse yourself. ENSO events are part of the natural climate variability and not a consequence of climate change. These events have been occurring in the past and will continue to eventuate in future. However, that being said, climate change does have an impact on ENSO events. Model projections show that El Niño events will become stronger and more frequent in a warming climate. This may mean that El Niño impacts may become more severe in some places, that is, either increased precipitation resulting in severe flooding or minimal precipitation resulting in severe drought conditions. Whatever the case may be, it is clear that climate change does have an impact on one of the main drivers of internal climate variability, and that the phase of ENSO may change in future. What we have learned in this session is that ENSO events oscillate between El Niño and La Niña events, and that they are naturally occurring events. We have seen how the atmosphere and ocean behave during these events, and what the impacts are on vulnerable Pacific Island countries. And finally, we have put into perspective how climate change may affect the natural variability of ENSO events in future. I do hope that you have gained some basic understanding of tropical Pacific climate and its variability through the example of the ENSO phenomena. There is much more information to be shared, as this session was just the tip of the melting iceberg.